Let's go ahead with micro milling. So in the first lectures, we have seen the basic equations. Now I give you instead a description, a physical description of the phenomena happening in micro milling. And first of all, we have to say that when passing from macro processes to micro processes, one should or could think that it is just sufficient to downscale. And in some ways, this is not completely wrong. You can downscale some of the aspects like machines, but there is a limit. Beyond that limit, the physics behaves in a different way, and so you cannot just reduce the scale because something different is happening. You know, if you look at the materials very closely, you know that you can pass from a situation where you can consider them as homogeneous, but then at a certain point at the micro scale, you see the grains, you see inclusions, and so you cannot consider them homogeneous anymore, for example. And in fact, the material plays a role on micro milling because it is still a mechanical process. So it exchanges forces with the material. And so what you see here at the top of this slide is a case where you are machining a material like consider cast iron, for example, that could have grains, round grains like this of graphite. And so your mill can pass through different grains with different orientation or even made of different materials. This happens at a scale where the mill could be could have the same amplitude, the same dimension of the grains, because sometimes the mill could be 0.1 millimeters, 100 microns, so you could have materials with that dimension for the grains. And in fact, in the first paper from literature here, you see that there is a fluctuation of the force, because on average, you have an average distance between the one type of grain and the other. And so when the mill is passing through, it feels a different resistance of the material. And this could be bad because the mill is suffering vibrations. And at that scale, you could have even bad problems of fatigue. And so you risk to break the mill for these reasons. In the second paper here, you see another effect. That is due to the orientation of the grains. In fact, in this paper, they machined copper, if I'm not wrong, but it is aluminium. It is a single crystal aluminium. You know that in metallurgy, you can let some grains grow, and you can even make a turbine blade, probably I've already told you, made of just one grain. So once you have that, let's say, perfect lattice, I have said last time that the material resists more. But in this case, the interesting fact is that if you put your tool in a different orientation with respect to the material, what you can detect is the fact that you are, let's say, soliciting different ways of the formation of the lattice. Because you know that depending on the type of lattice, the materials can be more or less deformable. For example, magnesium has really a small number of ways you can apply for deforming it, but still, depending on the type of lattice, BCC, for example, or others, can have a different ways. And what you can see here is that depending on the orientation, you have different forces, but in some cases, you could have even instability, because if you place the grain in a certain position where you are exactly, let's say, at the boundary between one way of deforming the grain and the other, it could be that the machining operation becomes unstable. We can talk about these effects as side effects. So side effect is an effect that comes from the fact that you cannot simply downscale. At a certain point, you see how the materials are internally organized. Then we have another effect, which is called in a similar way, but the name you can find in the specific literature is minimum chip thickness effect. Again, it is something coming from downscaling, but it is also something that can be seen in macro processes when you want to remove material with a macro, with a standard tool. In fact, maybe for the ones that have already attended manufacturing processes here, at least, you should have seen orthogonal cutting. Orthogonal cutting is a particular type of cutting where the forces that the tool is exchanging with the material are just bidimensional, not three-dimensional, but only two dimensions are involved. Because this is the direction of VC, which is the cutting speed. As I told you last time, VC, the cutting speed, is the relative velocity between the tool and the material. At least it is the main component of the relative velocity, because you know there is also another velocity, but the cutting speed is the biggest one. It is the most important one also for our calculations. So VC is here. The tool is moving like this, or the material is moving like that. We don't care. So we care only about the relative motion. And so the chip slides on the rake face, as I told you also last time. You see the basic dimensions that are important for us. This is the depth of cut, AP. The depth of cut is measured along the cutter. Be careful here not to confuse the depth of cut, which is this one, with the chip thickness, which is in the other direction. The chip thickness is measured perpendicularly to the cutter. Instead, the depth of cut is parallel to the cutting edge. Okay, this is the chip thickness. The chip thickness is the quantity that is connected to the feed per tooth that we've seen last time. But now, let's focus here. In a case like this, the forces are just bidimensional because there is a certain angle of the cutting edge respect to the material. For example, this angle here is perpendicular to the cutting speed. So if you imagine to take the cutting edge, there is no angle on this plane, but the direction is perpendicular to the cutting speed. It goes like this, so there is not an angle like this. Because you can imagine that if I have an angle here, the chip, instead of sliding this way, parallel to the cutting speed, would slide a little bit to the right? If I do this way, the chips will flow in this direction. Instead, we don't have it. And if the chip flows in this direction, there will be a force in this direction too, because there is friction between the chip and the rake face. Instead, we don't have a force in the perpendicular direction respect to the cutting speed, only in parallel to the cutting speed and perpendicularly, but in this direction. And in fact, last time, if you remember my drawing at the board, I told you that there is a force in this direction. What I told you last time is that typically in machining, the cutting force, which is the one that is parallel to the cutting speed, is the main one. So the same reasoning is happening also for the force. Along the cutting speed, there is the major component of the cutting force. But I told you that this component exists because my tool, in any case, is pushing a little bit on this direction. What happens in micro cutting in general is that, as we will see in the next slides, this perpendicular component can be bigger than usual, let's say. But at the moment, let's stay in the frame of the hypothesis, because I want you to focus on another detail. Typically, when doing this part in manufacturing processes 1, you make a tight hypothesis. What we say usually is that my cutting edge has a null radius, no radius. It is perfectly sharp, which in reality is not possible. You know, in mechanical applications, zero rounding doesn't exist. If you go there with a microscope, you always can measure a radius. In the best cases, where the tool is made of diamond, you could measure 1 micron of rounding. still 1 micron exists. The point is that in micro machining, the chip thickness could be of the same order of magnitude of the radius at the cutting edge, because sometimes the chip thickness is just 1 micron or less, or a couple of microns. Okay, so what we are pretending to do is removing a really thin layer of material. But our tool is always dull. It is always rounded, like this. When you have a situation like this, especially when, let's look at this one. Let's consider to have just this cutting thickness, chip thickness. You see that we are just involving the round part of the cutter. So this is just the rounding. So my chip will never see the rake face because it will be formed here. So it is like the actual, the real rake face when I'm cutting such a thin layer is this one, is the tangent plane to the rounding. And in fact, the chip here will feel more pressure. Okay, because it is like the angle is really negative. If you remember the convention I have introduced last time, I told you that you do the perpendicular line respect to VC, and then when the rake face is forming an angle that is more than 90 degrees, this angle is positive. And I asked you to associate this with, let's say, a better way of forming the chip, because when I have this angle, the chip forms better because the forces are lower. It slides easily. Instead, when I'm doing this, I'm pushing a lot. So the forces are increasing, I have more friction, and so the situation is worse. But the issue is that in micro machining, since we always have a rounding at the tools, because even if I'm good in making the tool, as I said, I have some microns of rounding, but the chip thickness is of the same order of magnitude. What happens is that if I'm forming the chip, is that the situation is, let's say, more critical. I'm pushing a lot, I'm plowing instead of cutting, instead of just shearing, I'm pressing a lot. And in fact, we can identify 3 situations. This one is the same one of the previous slide. So here, at least, I'm forming the chip. Obviously, in macro machining, what happens is that in most of the cases, the chip thickness is much bigger. So we neglect the situation that we have at the rounding. So because most of the chip is formed exactly on the rake face, which is good. So we don't have to consider this effect. But in micro, we must do that. So typically, we are in this situation where the chip thickness maybe is, let's say, more than 40% of the rounding. In fact, if we do experiments, it is not written there, but I tell you, it is written in the notes of the slide. If we do experiments, what we see is that the chip starts forming when the chip thickness is at least 30–40% of the radius here. The name of this radius is RE. Okay, so I have difficulties, but at least I'm removing material. But the things can be worse, because sometimes, or in many cases, what happens is that we are at the chip thickness that is smaller than the minimum chip thickness. So TC min is the minimum chip thickness, which is 30–40% of the rounding at the edge. If I am in the second case, TC is smaller than the chip thickness. So for example, 20% of the radius or 10%. And here also, what we are doing is plowing, so plastic deformation, plus elastic deformation, but without forming the chip. So it is like I have a wave here, but then I'm smashing that wave on the surface. So I'm not removing any material. A part of the energy I am placing there is stored in the material, like plastic deformation. So for example, I have a strain hardening. So I'm creating another surface without removing anything. The rest of the energy instead is stored as elastic energy, which means that as soon as my tool will go away, I will have the so-called spring back. So the surface will go back elastically, and this is detrimental because the surface will slide with friction on the flank face of my tool. So this is the rake face, and this is the flank face. So the material is coming back, and so I will have friction, which is the friction responsible, the main phenomenon responsible for the tool wear. So much of the tool wear happens here on the flank. And this is in the middle. But then there is another situation where the chip is even smaller than the elastic field. So this TCE, this E stays for the limit. It is corresponds to the yield strength of the material. In the case, not in terms of units, this is a chip thickness, but that situation is at the limit of the elastic field of the material. But so, which means, and this is the reason why I have both the elastic behavior and plastic, because I am above that limit. But if I go under the limit of the elastic limit, what happens is that I only have the elastic behavior. So basically what I'm doing is nothing on the material, because the energy is stored elastically and then my material will spring back. But in any case, I'm paying for this situation with tool wear, because when the material springs back, it slides with friction on the flank face. So after this discussion, I can say that we should always verify that the parameters that we have selected, and we have made these calculations last time. So the chip thickness, we call it the chip thickness as H in the formulas. I'm sorry for this nomenclature, but it is good that you see all of the nomenclatures. You can find both TC or HD, depending on the nomenclature. This one comes from my colleagues in the United States, and they use another nomenclature. According to our nomenclature, the chip thickness is called as HD. It is there. I show you here. HD. It is not written here, but this is HD. Where you see D, it means nominal or uncut. In fact, another way of calling this thickness is uncut chip thickness. Why uncut? Because it is the nominal one before the cutting action. Because after the cutting action, the chip thickness you see is different, and typically it is bigger, because it feels the plastic deformation that happened inside the chip itself. So for this reason, it is getting thicker. And the plane across which the chip is formed is called the shear plane, and this one is the shear angle. This is the nomenclature coming from the orthogonal cutting. Now, we have already seen this video, but now I'm using for another purpose. It is not so important, but why not? So there you see the animation, and here I have just stopped where there is a clear formation of the chip. You see, for example, the effect of the helix angle. If you remember, I quoted the helix angle. You see that because of the helix angle, the chip is flowing up. For the same reason I have described in orthogonal cutting. Milling is much more complex than orthogonal cutting, at least because I have more than one cutting edge involved or on the tool. But the basics are the same. So here you see the representation of the cutting edge. The cutting edge is this one. It is long and it is an helix, a cylindrical helix. And in milling, you know, the cutting speed is the tangential one. In milling, this motion is associated to the mill. If we take a look here, I can use the information I have got thanks to the slides before, because I could cut my chip thickness into slices, and at every slice I could consider that the angle gamma, which is gamma 0, the rake angle, or gamma n according to the nomenclature in the United States, you know, for the slices that are taken here along the rake face, I have the nominal angle. But when I come here, I have the so-called effective rake angle, which is negative because of what I have told you before. So I'm just saying that what happens in orthogonal cutting happens also in milling. But in milling, I have another issue, which is this one. Somehow I've already told you, because this drawing is exactly the same that I have made on the board last times. So these are the arcs that are accomplished by each cutting edge. You know, the distance between one point and the corresponding point on the other track is Fz. So it is the same discussions we have made. And if you remember, I told you that here I have a chip thickness that tends to 0 at the beginning. So if you imagine to have a mill here, when the cutter of the mill enters into play here in contact, the chip thickness is null. So what happens is that we have a very negative effective rake angle, and we are not removing any material for what we have just said, because the chip thickness is too small. So the rounding is such that it is just pushing, which means that for a certain length along the engaged arc, nothing is happening. The tool is just pushing. Only when the chip thickness overcomes the minimum chip thickness, finally I'm removing some material. Which means that in milling, obviously, in a situation like this, where I have selected an Fz that probably is very small, I'm removing material only in the middle, where we know that the chip thickness tends to be equal to Fz, but at the boundary, at the entrance and at the exit, the chip thickness is too small, which is something a little bit misleading, because how could it happen? For example, what I can say is that it is like the material is piling up, because you know, here I have a cutter that is not moving anything. Now the next cutter will come. In the meantime, the center of my mill has gone ahead, right? Because my machine is going ahead. It is continuously working. The machine doesn't know anything about what is happening. So in the meantime, my mill is bending because the tip has not been able to remove material, but the part that is connected to the spindle has gone ahead. So it is like a spring. It is like I'm loading a spring. So because of this elastic behavior of my mill will push more. Moreover, since I have piled up this material, at a certain point, this stack of layers is enough for finally removing the material. So what happens is that I am removing material only only after a certain number of revolutions. Because I do the first one, I'm removing anything. The second one, and I'm piling up the material. The third one, and so on. At a certain point, thanks to the elastic force of the mill that has been loaded by the fact that my cutting head is moving ahead. Moreover, now I have a certain stack of material to remove, and probably I have overcome the minimum chip thickness. Finally, I can remove the material. But be careful, because you could imagine that you could solve this issue if you select an Fz that is big enough. In reality, it is not like that, because even if Fz is big, for sure you overcome the minimum chip thickness at the center, where the chip thickness is high. And if you increase Fz, you know, the two tracks are creating a bigger chip thickness. But in any case, at the entrance, at the exit, the chip thickness will be always null, will always tend to 0. So for this reason, when you see a milled surface, if you look better at the sides, for example, if you look at a slot milling operation, in the middle, you probably will see good striations, because a good milling operation must leave striations. It cannot be perfectly flat. But at the boundaries, a blurred surface, because the chip thickness in any case will be so small that the mill is smashing the material. Okay? I said that you never see a mirror-like surface. In reality, if you select a really small FZ and you have a really good tools that are really sharp, for example, diamond tools with a radius of about 1 micron, on aluminum, you can have surfaces that are like a mirror. So the striations exist. So the milling operation is good. So every cutter has left its striation, but the order of magnitude is so small that our eye and also an instrument measures a roughness that is some nanometers by milling, but you need to select the right tool. In any case, this phenomenon is always happening in macro milling and micro milling, macro and micro. Now, another phenomenon that is well known in milling is the built-up edge, which is a behavior that is represented in this micrography. We obtained this micrography in our laboratory with a special equipment. Because, you know, for obtaining this, you have somehow to freeze the cutting action, which is not easy. In order to freeze it, what we did at that time was building a system for quickly removing the tool from the workpiece. And for doing that, there was a piston loaded with compressed air. And so we triggered the piston in order to release the energy and in order to let the tool rotate. I'm cutting the story short just for saying that, just for obtaining these micrographies, it is a long story. Once you have the part, then you have to put it into the resin, then you have to grind it, and finally you can see these at the microscope. So a long story. In reality, on the internet, you see some guys, some researchers that have placed on a lathe, for example, an high-speed camera, and they are able to see something like this. What they do is grinding the material before, and then they just look at what is happening. Instead, in our case, first we were doing the cutting operation, and then we put into the resin in order to grind and to see this. And we selected the material where it was possible to see the grains. This was a C10, if I'm not wrong. Yes, C10 steel. So you see the grains here, and you see that when they pass through the shear plane, they are stressed. So there is a shearing action, okay, across the shear plane. So this is just for telling you that what we see in the graphs happens in reality. The built-up edge is a material that instead of staying with the chip, sticks on the surface of your tool, on the rake face. And in fact, now it is not possible to see, but if you take the slide and you amplify, you would see small layers here. It is like, due to the pressure that my material is acting, is applying to the rake face, the material tends to strain harden, and so it is not easy to let it slide along the rake face. This happens also in micro, also in micro and in macro. What we always do in macro conditions is increasing the cutting speed, because you know when you do it, when you increase the cutting speed, you are also increasing the temperature. And if you increase the temperature, you relax this material, and instead of having the strain hardening, you let it flow better. So it is a good action to increase the cutting speed in order to exit from the area of the built-up edge. If you take a course of manufacturing processes 1, you see this. They tell you that it is better that the cutting speed overcomes a certain minimum level. Otherwise, you have the built-up edge. But what happens in micro is that instead of removing the built-up edge, it stays there. These 3 slides, three pictures have been obtained with an increase in cutting speed, but it is still there. In fact, in microchip removal, not only in milling but also in turning, we have a new concept. The built-up edge tends to be stable. It remains there. It is like you know, a dummy portion of the material. If you remember extrusion, in extrusion, you know, when you have a billet that has to pass through a smaller hole, if you remember that part of manufacturing, you know, there is a certain part of the material that remains there. It is like the material finds its way to slide. What I'm saying is this. The material tends to slide like this. It happens also in fluid dynamics. But let's imagine that this is an extrusion operation, and I have a billet in the middle, which is made of hot steel. Here, the material is steel because by nature, the material will slide along these internal surfaces, and I can call this portion of material dummy, a dummy portion. And this happens also here. So it is like the built-up edge is creating a cap around the real cutter. In macro condition, we always say that this is not good because it breaks. And when it breaks, it is so hard that it creates troubles to the finishing operation because some inclusion of the built-up edge will remain on the surface, and they are much harder, maybe 3 times more. So when you pass with the finishing pass, you break the tools that will come. But in this case, it stays there. Moreover, there is also a positive fact, because if you compare the inclination of the original nominal rake phase respect to the fictitious, or better, the real one that is happening now because of the presence of the built-up edge, this is more positive. So the built-up edge somehow is helping us to form the chip because it is creating a more positive angle respect to the original tool. So in micro conditions, always we have to fight with these issues. In fact, even the models can consider this. I just give you some details because the theory behind is complex and exits from the purpose of this course, but this is the original model by Merchant that probably you have seen in Manufacturing Processes 1. This is the shear angle. And one of the main hypotheses of Merchant was that the cutter has a null radius. It is perfectly sharp. And so the things were easier. Instead, this model considers the tool as round, and it also considers the presence of a dead metal cap. This is also a name used for this dummy portion of material. And if you look at this, it seems that the material has created its own cutter by putting there some material that at the end is creating a couple of surfaces along which the chip will really flow, like it happens in extrusion. And a model like this considers that there are chunks or portions of material that are sliding along some planes. This plane is the shear plane, like it exists here, but there are also other planes. So this makes this theory complex. The good point of this theory is that it is able to separate what is happening along the rake face, considering also this side of the dead metal cap, So this model calculates the two forces, the one parallel to the cutting speed and the perpendicular one for the shearing action, but it is also able to consider this side of the dead metal cap, where the action is mostly a plowing action. But it is like the model is able to decouple the two situations, so two forces here, two forces here. We also did research on this and we validated the model. The model is complex, but it is more suitable for micro milling. The reason why I am presenting it here without entering into the details is for telling you that both the experiments and also the theory are, let's say, consistent in saying that something different is happening in micro because of the rounding. So everything started from the minimum chip thickness effect. So if we want a very precise model, we have to change or to remove an hypothesis of merchant. Someone in literature did also some other experiments. For example, these are experiments that are called molecular dynamics. It is a way of simulating the behavior of materials. It is like every dot here is a molecule of a material, and this kind of simulation is able to represent the forces that every small portion of material is exchanging. It is at a very low scale. Then a paper like this should prove that this happens also in macro, but let's take just what is important for the lecture. If you see, here I have a higher density. You see a couple of lines. So somehow the molecular dynamics seems to confirm that there the material is sliding along different planes. This is just an information. So for you to know that there are simulations that are able to do that. And also here you see some experiments, you see a kind of dead metal cap. But I think that these graphs are even better because they are confirming what I was telling you about the way of simulating the microcutting action, because you see the two sides of the dead metal cap. And what is important for us in the frame of the lecture is that when the ratio between the chip thickness and the radius at the cutting edge is too small, I have a negative effective rake angle. So this is confirming what I have told you from the beginning. Since it is round, the tool is round, it is just pushing. And my material is feeling a negative rake angle, which is not the nominal one, because I'm just acting on the rounding of my edge. Instead, when the ratio becomes 0.6, for example, which is higher than the critical value that was 0.3, 0.4. At 0.6, the chip must be formed. And in fact, this inclination now is positive because the reference is always the vertical or better, the perpendicular respect to the cutting speed. In this case, it is positive. If I go to 0.9, it is even better. It is even more positive. This is just, again, for saying that both experiments and modeling are consistent. So what we have to do is overcoming the minimum chip thickness. Otherwise, we are in troubles. Maybe at the end of the lecture, I will learn that the computer is here. And I can add also something more now, because in the top graph, you see the cutting force. The cutting force is, as I said, along the same direction of the cutting speed, which means that the material is flowing this way. And so this is the force. But now let's take a look also to the feed force. FF is the feed force, the perpendicular one. What we can see is that if I put on the x-axis just the ratio between the chip thickness and the edge radius, this is the ratio that is important for us, you see that the cutting force doesn't feel anything. So I start from a small value and it is continuously increasing. Yeah, maybe a little flat portion here, but it is like FC is not feeling anything about this transition between the negative effective rake angle and the positive one. But if you look at what happens to the FF, to the feed force, you see that instead, when I am lower than 0.4, so I am not overcoming the minimum chip thickness, and we know that we are plowing, what is happening is that the feed force is feeling this effect, this plowing effect, and in fact it increases. As soon as I overcome the minimum chip thickness and finally I can form the chip, you see that FF remains small, and yeah, it slightly increases, but it is not feeling the increase of the chip thickness. So if you remember the formulas that we have seen last time, we know when we calculated the FC based on the chip thickness, and this remains true. But when my chip thickness is too small, I cannot forget that there is the other component that sometimes can be even bigger than an FC, because I'm plowing a lot. I'm pushing a lot perpendicularly to the surface, because this is round and it is pushing. Okay, consider that every dot here is a different condition. It means that I organize an experiment where I have a certain chip thickness, that then I measure the forces, then I stop the operations, and I do another experiment with another chip thickness. So this is not continuous. These are different experiments. And I can also say that if we use the basic theory, where everything depended on the shear angle, if you look at the merchant phi, the shear angle was responsible for everything happening in orthogonal cutting. But you see that phi is not feeling any transition. Again, it increases slightly. Instead, if we look at the effective rake angle, the effective one is the one that is taking care about the negativity of the rake angle at the rounding. Here there is a step, which is another confirmation of the fact that a model, for being correct, should consider the effective rake angle and not the nominal one, because the nominal one is not involved or is not so important as the effective rake angle, because in micro it is not so probable that we have a chip thickness that involves more the rake phase respect to the radius, because the chip thickness is small. Now I just have to add what happens in milling, because those experiments, as I said, were experiments that I can do in orthogonal cutting. But now if I go to milling, I have the same behavior of the thrust force, FF, or the feed force, and the cutting force, so I'm not adding anything. But it is good to see at these graphs where every dot is a revolution. Okay, there is one cutter that is making its revolution, and I'm calculating the average force of that pass. And we have the thrust force in black, and the empty dots are the cutting forces. If I am selecting an FZ that is well bigger respect to the minimum chip thickness, I'm minimizing the effect of the minimum chip thickness just at the two sides, at the entrance and at the exit, if I am doing a slot milling. But since I'm calculating an average force, I see that this is a good condition. It is a standard condition where the cutting force is bigger than the feed force. So everything is as expected. So this is a typical macro condition. Instead, in micro, look at the behavior. Since TC is really small, and maybe it is much smaller than the minimum chip thickness, what happens is what described also in orthogonal cutting. So at every pass, I'm increasing the feed force. You see that it increases, but at a certain point, finally, I am able to remove the chip, and so it goes down. And the empty dots are the cutting forces and you see that also the cutting force is increasing, but it is always smaller than the feed force. Everything depends on the fact that I made the wrong choice of the parameters. I shouldn't have selected such a small FZ. And this is practical, because maybe you can tell me, yeah, you are doing this story too long, at the end I just have to mill. Yes, but if you mill, and sometimes you follow the indications of some catalogs that are not correct, you break the mill because the mill cannot do the job. If you select a too fine FZ, this is a little bit counterintuitive. What I'm telling you is that it is true that the milling tools in micro are delicate, but we cannot exaggerate in reducing FZ. Otherwise, we are not cutting anything. And then we break the mill because the feed is too small. Because one could expect that you break the mill because the feed is too big and the FC is too much, which is true. I also break in that case. But maybe you cannot expect that there is also a lower limit. So what I'm telling you is that we have to be careful about the lower limit too. And this slide describes also experimentally what I was telling you before. At the first round, I'm not removing anything, but my mill, my spindle is going ahead, so my mill bends. I do another passage, but I'm not removing anything because I have selected a chip thickness that is always smaller than the minimum one all along the edge arc. So it is a bad mistake. And this graph is telling me that if I do an experiment like this and I collect the chips that has been formed, in this research, they saw that the chips were 9 times thicker than expected, than the nominal chip thickness. It is like the chip was forming every 9 passes because it was piling up, and only at the 9th pass, finally, the cutter was able to remove the chip. But by itself, maybe it is not an issue, but look at the mill. The mill is continuously fluctuating. It is continuously bending and then recovering the deformation, which means that it is vibrating along the feed direction. So it is going ahead, but it is continuously moving like this. And it is easy to break a mill in this way because it feels fatigue conditions. So if you want to exit from this situation, you shouldn't slow down, but you have to go faster, which is counterintuitive. But instead, this is the case because the feed was too small. Now, let's go ahead with the other effects because we have a long list. The ones that I have dealt with till now are the most important ones, but we have also some other side effects typical of high precision manufacturing, because sometimes I have used micro milling, but also high precision needs this. So mechanical deformation. So at the beginning, if you think about a macro situation, the mill is like something really stiff, really big. You cannot expect that it deforms, but this is not true. So especially in high precision and in micro milling, everything is deforming, the mill and even the workpiece. Because if you are milling a thin wall, you can expect that the forces are such that both the mill and the wall are deforming. In fact, a good rule of thumb in milling is using the biggest tool you can use. So, in other words, if I have to make a thin wall, but I have space, plenty of space laterally, it is better if I use a big mill. The only point that we have learned today, that mill can be big, but it has to be, what would you say? Big mill, but the cutters should be
really small rounding.
Right, sharp. Sharp. So if you have a big mill, maybe 10 millimeters, I have to make a wall of 1 millimeter. I can use a mill of 10 millimeters, but it has to be sharp. So the cutter must be really fine in terms of rounding at the cutting edge. If you respect that condition, even a big mill does a good job, and you have a big advantage because it doesn't vibrate, probably. It doesn't bend, so you are sure about where it is. Obviously, on the other side, if you are milling a thin wall, that wall will bend. But there are some strategies in order to save it. I was talking before coming to the lecture this morning. I had a meeting with some colleagues of CNR, making filters for gigahertz transmission in the space. Okay, very fascinating application. At the end, what they want to have are small channels of, let's say, 80 microns, really sharp, because when the waves, the electromagnetic waves, pass there, they are somehow filtered. I'm cutting the story really short. But with micromilling, but also micro-EDM, is inside of that course, this course, you can make those fine geometries that are acting on the electromagnetic waves and are able to filter them. So you see, this is nice because you see how the geometry of a part made on aluminum, because they tell me that in the space they prefer to have aluminum instead of silicon, because silicon is fragile. And this part is small, but not too small. It is some millimeters. And a piece of silicon of some millimeters is too fragile, right? Do you know why it is too fragile? This is somehow connected also to the behavior of the mills. If you have a thick piece of a fragile component, why? You risk more to break it respect to when it is fine, it is thin. You know for sure the theory. Maybe you haven't applied to this case, but you know why. You just have to find. It is a bending action, right? When you bend, you have to achieve the ultimate tensile strength of the material. But if you remember that formulas, you need the distance from the neutral axis, right? But what happens if you have a fine layer of material? If the layer is too fine, you never achieve the ultimate tensile strength. This is at the base of the reason why glass fibers are difficult to break. Only if you apply a very small curvature, you break them. Otherwise, you can bend, even if they're made of glass. It's not a joke, it is glass. But when it is thin, you cannot achieve the sigma for breaking it. Okay, so on the contrary, they don't want to have a big piece of silicon because when it is thick, it is keen to be broken. Instead, they prefer aluminum. Then thermal deformations are important, especially because of the environment. Because remember that if you have to make a really precise part, you should be aware about what is the temperature at which it will be used. Let's go ahead with this example in the space. If they tell us that that material has to work at, I don't know, 0 degrees Celsius in the space, what happens if I machine it at 20? Or even worse, because the machining creates temperature. What happens if I'm machining that curve at, I don't know, 50 degrees Celsius? It will be larger. And then when it goes back, I don't know if it will stay in the tolerance. So be careful about the thermal deformations. It is true that the modern machine tools are cooled down everywhere in the axis, in the spindle, but this still is an issue. For example, when you want to be more precise, it is good if you take your part and you leave it there for a certain amount of time at the right temperature. I don't know, at 20 degrees. Yeah, you cannot take the rough part from the truck at, I don't know, 35 and put it on the machine and pretend to obtain a micron level precision. You have to wait for the equilibrium. Surface integrity is roughness, in other words. In roughness and other things like residual stresses, everything is happening at the surface. Also here, we cannot scale down everything. So at a certain point, we have side effects. So for example, we have talked today about plowing. Plowing is getting a worse surface. So if I want to obtain a nice surface, I have to switch to other solutions, like I have said, a diamond tool, which is really sharp. Otherwise, I cannot obtain the work, the job done. If you remember the Schmalz formula, there was a formula, yeah, we have seen in the last lecture. for calculating roughness, array roughness. In that formula, there is the feed, but you cannot use that formula everywhere because at a certain point, it is not true anymore. When the feed is too small, something else is happening and that model is not valid anymore. So I'm just telling that you cannot downscale everything. The last point is also very important because when you want to reference a part on a machine tool, what you do in macro is typically, if you have a squared part, you put it in contact with the reference surface. But what happens if your part has, I don't know, a side of 1 millimeter? It is weak, so you cannot position it perfectly. And even if you have a grain of powder, you have a big error in terms of angles. So the best solution in micro is never removing your part from the machine. So for this reason, it is better to have a 5-axis milling machine because you take the part at the beginning, you machine everything, and then at the end you cut it. If you look at our site, Polymill is the name of my laboratory. There is a component that we made for the Dynamis team, which is called the A-arm. It is a joint where they attach the links of the wheels. And that component is a complex one. And so you can have an idea, because there what we did was just blocking a block of aluminum. We machined it everywhere, and we left only a thin wall. And so with the last pass in hot milling, we reduced that thickness at the value that you can go there and you can take it away by hands. Obviously, you will see something there, but if you selected the right position where to put that wall, everything else has been machined without removing the part. So you can replicate the precision of your machine. So if you have a good machine, you stay at the micron level. Some microns, let's say. Then burrs or flashes. In mechanical terms, this is a burr. You know, when it comes from a thermal action, sometimes it is called flash, or even when it is made of plastic. In any case, these things are really detrimental because, as you can see here, sometimes they are even bigger than the features that we are machining. So there are some solutions. A simple one is passing again on the same surface at a 0 cut in depth so that you remove it. Or someone is using some other cooling fluid like CO2 or liquid nitrogen in order to, let's say, freeze the material. Because when the material is at a low temperature, it is not so tough, and also it doesn't flow so well, so it breaks. So it is better to machine. When a material tends to create burrs, if you freeze it, you are creating a kind of brittle behavior, and brittleness is better in terms of burrs because you break the burrs. There is also a side effect. When the material is too brittle, like ceramics, what you risk is that instead of having burrs, here you could have some small craters, because instead of cutting, you are breaking the material. So as always, we have to stay, let's say, in the middle. Let me say something about cutting hard and fragile materials, because it is this lecture the good opportunity to say this. Micro cutting can do a nice job even on glass, even on ceramics, because there is a good point of what we have seen about the big pressure that we are applying when plowing, because this is something that you should have studied again in metallurgy. When you have a fragile material, but you put it under pressure, and it is better if you have the same pressure you could have at the bottom of the sea. So it is pressure in all the directions. Even a fragile material tends to behave like a ductile one. It is like the pressure helps it to be tougher or not to break, let's say. The ultimate tensile strength increases, but in terms of chip, you can even create a fluid chip the correct name in the field is ductile chip, even if you are machining a fragile material. So this is the good side of putting pressure on the material. This is also used in macro cutting. For example, if you have to turn an hardened bar of material, I don't know, at 55, even 60 HRC, so really hard, you can use a ceramic insert, and that insert will have a negative rake angle because it will push. And this is something good on a fragile material because you will let it behave like a ductile one. So this sounds as the contrary I have said till now, but till now I was talking about ductile materials. And this is also, from my point of view, the beauty of manufacturing. There are no, so the rules are valid for certain portion of materials and tools, but then you have to be open to change mind where the conditions are different. Obviously, this creates difficulties, but you know, in the difficulties you have the added value, because if everyone is able to do a job, the value of that job is not high, right? So, especially in industry, in the Western countries, we must work where there is added value, and for sure, those are difficult jobs. Other side effects on the side of the tool is really, let's say, fragile, but not so fragile according to what I have said. When you have a thin mill, it is fragile for sure, but it resists to bending because of what I have said about the glass fibers. So its diameter sometimes is so small that it is not so easy to break it. If you go there with your finger, you break it suddenly. You didn't, you cannot understand even if you are touching it. But if you adjust the parameters, it is robust enough. So this is the list of bad conditions. Chip clogging. Chip clogging happens, for example, in drilling, when the chip is not evacuated correctly. If the chip remains there, you are it is completely stuck in the flutes of the tool, and so the force will increase. And since my machine is not sensorized, the machine doesn't know anything. It is going ahead. And even if there is the chip clogging, it will apply a feed at a certain point. My mill will break because of buckling condition. My mill or my drill bit, if I'm drilling an hole, at a certain point, the feed force is so high that it bends and it breaks. So buckling is the typical buckling that you have studied in other courses. Fatigue, again, since it is rotating, and since there are effects like the ones that I have described today, the forces are continuously varying. So if you don't select the right parameters, you break the tool very easily. And also run out is important. You know, run out is the error according to which the axis of your tool is not perfectly aligned with the axis of the spindle. So your tool maybe is doing something like this instead of rotating along its axis. And if you are in that condition, the cutting action is not well distributed between the two cutters. I have an animation about that in a while. This slide is just for saying that if you want to overcome all of these issues, you not only must have a good machine, you have to study a right fixture, you have to select the spindle and the tool holder correctly, but then usually you must have also a layer of instruments that are applied to the machine in order to acquire information about what is happening. So, for example, when you place the part, then the current machines have a touch probe. It is a gauge which is placed on board in the spindle. So your machine can go there and it can touch the wall, and this way you can store the position of the workpiece. Instead, in the past, it was a difficult story because I don't know if someone has this experience, if some of you has studied in the previous schools by using a lathe or a milling machine. Maybe you know that they went there with a piece of paper, and when the mill was able to move the piece of paper, it was this was the time to take the zero condition, because the mill was close to the wall, less than I don't know, 0.1. So this is the accuracy you can have if you go by hands. But if you go with a touch probe like this, you are at a micron level, so some microns, maybe 10 microns, let's say. And also you have a system also for measuring the tool on board of the machine. Instead of measuring it outside, you measure it when it is rotating, before cutting. You let it rotate so that if you have run out, this system is able to measure run out. So I can stop and I can replace the tool. And then there are also some visual systems. For example, in our laboratory, we developed a system for, instead of touching the part, for keeping the picture of the part in order to center an hole in a small wire, in a small circle. So measurements are fundamental, and monitoring. This is an acquisition made by a visual tool setter. So you go there with the tool, and since you are taking the picture of the tool while it is rotating, then you can measure both the diameter and also the run out. When you have run out, what happens is represented in this graph. It is like one radius of this cutting edge is smaller than the other. So with this situation is such that the cutting edge, which is more exposed, is removing much more material, and instead the other is removing just a tiny portion, which means that the action of the mill is not balanced, because when it is the turn of this cutter, my mill will feel more force, it will bend more, and in the other case it bends less. Not only it bends, but maybe I break it, because I didn't select the parameters for such a big chip thickness, but it is happening because of the run out. These are some signals acquired with a load cell, and these are the three components of the force. You detect run out when the peaks are different. For example, here they are different, but the difference is really small. So if I'm measuring the force, I can detect run out. But it is better if I start by measuring at the beginning. I have to start buying the right machine, buy the right tool holder. Then I cannot save money on the tools. The tools are the interface between the machine and the part. So I have to spend that money for the tools, and then I have to measure them. If I respect all of these steps, I'm pretty sure that everything will go smoothly. Regarding the measurements, we have also the possibility to acquire information with a machine like this. We have just renewed this. We have installed the new version of this machine in our laboratory a couple of days ago. So now we have a micro CMM coordinate measuring machine, which is just optical. So this is not touching anything, but look at what you can do. This is a cutting edge of a mill. You see striations because, you know, when you do a mill, when you produce a mill, you use grinding. So those surfaces are ground. So the edge comes out as just the intersection of two ground planes. So in many cases, the tool manufacturers do not have a nice control of the rounding, but we know that it is important for us. In fact, the most advanced tool manufacturers apply a treatment here in order to make it smooth and constant. With a machine like this, we can acquire here a bend. This bend is made, for example, by 100 lines, and then we can calculate the mean value of the rounding. This is the acquisition, and so we can measure the rounding on the tool. The same rounding we were discussing about can be measured by a system like this. And also here, this is also nice. This is the exit side of an hole where some burr has been created by the drill bit. If you go with a machine like this, you capture the 3D cloud of point, and then if you section, you can measure the burr like this without touching the part. The machine we have now is a 5-axis machine itself. So even the measuring machine is a 5-axis, because when you take the part, you can measure all the surfaces you want, and then you can verify the tolerances, you can acquire even the texture, not only the roughness, but I can describe in 3D how the surface is made, which is functional in many cases. Now, some words about the equipment. This is the last part of the lecture. In reality, I have also, yeah, I will try to conclude it. Have you ever seen this? Do you know the difference between accuracy and precision? So, since you say yes, I go directly to the next question. In your opinion, is it easier to correct a bad accuracy or correct a bad precision? I know that only a couple of guys said yes about what they are, but maybe I do a small recap. Accuracy, by definition, is the difference between the real dimension and the nominal one, the target one. You know that the target one is an unknown. Even if we measure it, since every measurement system applies an uncertainty, we know that we will never know the true value, okay? So it is something that exists, but we cannot measure. But in any case, after the measurement, the rule of thumb for the measurement system, you know, is that the uncertainty of the metrology machine should be 1 order of magnitude less respect to the dimension I want to measure. So, for example, I want to verify a tolerance of 0.1, 1/10 of millimeter. It is better if my machine has an uncertainty of 1/100th of millimeter, 0.01. It is a rule of thumb, but it works. And it is also applied in practice. So once I do that, for example, that optical machine has a micron level precision. So if I want to measure something of 10 microns, I'm safe with that machine. And I can consider it as perfect. I measure my dimension and I see that I have a distance. For example, this case. So I wanted to stay there, and instead, with the dots, what I got was an average distance of my dots respect to the target. This is a lack of accuracy. It is accurate when it is like this, when the average value is exactly at the center. Instead, precision is when, or a lack of precision is when I throw many darts and I'm covering a big area. So there is a distance between them. They are not all concentrated in a position. This is a symptom of high precision. High precision, bad accuracy. Okay? And instead, let's look at this one. This one is high accuracy because the average value is in the center, but low precision because it is spread. You can also see this spread as a Gaussian distribution in 3D. It is like I have a Bell distribution here, which is large. Instead here, my Gaussian distribution is thin. So precision is how wide is my normal distribution. If it is wide, I have a bad precision. Then let's go back to my question. It is easier to correct this situation or, I don't know, this situation, where the points are spread. In your opinion, why the accuracy is easier to correct? Obviously, you can bring this information from the measurement courses, if you have done that. Why is it? Perfect. This is a systematic behavior. Why is it systematic? Because you see that I have thrown many darts and they go every time they go there. So there is something in my machine, I just have to align it. If I correct it, I am in the center. So it is an offset, or as he was saying perfectly, this is a systematic behavior. And it is easier to correct the systematic behaviors. I have to detect them, but it is easier. Instead, this is a random error. In fact, the Gaussian distribution well describes this behavior, but it is difficult. Since it is random, there can be many causes that are overlapping. It is a lack of let's say, precision in many points, and summing everything at the end. I don't know, my lathe is creating a bar that has a random distribution in diameter. It is very, very difficult. So sometimes where the machine are bad in terms of precision, it is better to change the machine. So maybe that machine is good to satisfy a certain tolerance, but if I want to be more precise, there's nothing to do with that machine. I have to go on another one. Instead, if I am here, I have the possibility to correct it. Then let's see some examples. We have two machining centers. This is one. And look at the precision on the workpiece, plus minus 2 microns, which is good. I always say that the machine is able to do that, but then if I select the wrong tool holder, the wrong tool, the wrong parameters, I will never arrive there. So you don't have to think that you push on the green button and you obtain that precision. The machine potentially can do that. And the standards are telling me the performances. Let's say the thing that is closer to the concept of precision are these scatter, positioning scatter. It is telling me that if I tell the machine to go there many times, I have this distribution, this let's say amplitude of the normal distribution. They should tell me if it is 1 sigma, 2 sigma, or 3 sigma. In any case, this is the distribution. It is the sigma. And this is the other machine. The first one is a German machine. This one is a Japanese one. And we have just reinstalled it because we had another one. Then the representative in Italy substituted that machine because they have sold it. Now they have taken here the new one. I would underline this performance of this machine. This is the last input increment, which means that this is the smallest step that my machine is able to accomplish. But then if you read the numbers are, let's say, at least strange, because these are in millimeters, and I have 1, 2, 3, 4 zeros after the comma. So these are 10 nanometers. So I can tell my machine, go ahead by 10 nanometers. Or if I speak in microns, in this position there is micron. So it is 1/100th of micron. So I can tell my machine, go ahead by 1 step of this dimension. And it does that, it controls that. Then I'm not saying that we can do a part with that precision, but I'm saying that the machine controls that. Then I have to sum all of the other uncertainties I have. But if you start from there, we have also done parts in the micron level precision. On that part I was citing before, there was a nominal dimension of 11 millimeters, and we did many times 11, 0, 0, 0. So 0, 0 micron, sometimes 0, 0, 1. So the micron exists, but it is difficult to get, and we have to start from a machine like this. Then also the tools are, as I said, fundamental. Consider that some tools cost, for example, the diamond one cost 400 euros each. Maybe the diameter is 1 millimeter, 400 euros. So it is expensive, for sure. if you don't know how to select the parameters, you break it at the first touch. So everything is complex. But instead, if you know how to do, you do parts that cannot be done in with every other type of process. So why do these things exist? Because they are helpful, they are needed in some fields, not everywhere. So I'm projecting this table because it is one of the best ones I have seen in terms of parameters. So they declare the revolution speed according to a certain diameter, because let's remember that the parameter is the cutting speed. They suggest me the depth of cut, AP, AE. This is a diameter of 100 microns. Let me see. What else? They suggest the VF, the feed rate. These are the same terms we have seen in the formulas. Another interesting fact is the hardness of the material this mill can machine. Look at this one. Hardened steel, 68, 72 HRC. 72 is crazy. It's a crazy hardness. So absolutely hard. When you do tempering, when you arrive at 58, it is already a good 58, is already hard. This is 72. So these mills can do a nice job. Obviously, they wear out as the other mills, and you will risk to break them easily if you don't select the parameters. And here we have also the parameters, the feed per tooth, FZ. This is in inches, and this is instead, no, this is millimeters per revolution, these are inches. So these are 32 microns, which is small, but not so small. The reason is what we have seen at the beginning. I cannot exaggerate in a small chip thickness, otherwise I cannot cut, okay? And for sure, when you see the parameters on a catalog, the first question you should ask to yourself or to the manufacturer is 32 microns, but are you sure that the radius on the cutting edge is less than 32 microns? I can say yes in this case, because we measured the cutters. They can have a radius of 4 microns. So this is well beyond, so this is good. But it happens sometimes on some catalogs that you can find FZ equal to 1 micron or 2 microns. I cannot trust on that parameter. It is wrong, for sure. You cannot cut with an FZ of 2 microns. Or you should have an incredibly sharp tool, which is not the case. Yeah, then tool holders, but now I can go fast here. Tool holders are the interface between the spindle and the tool. So sometimes runout come from the fact that I have selected a bad tool holder. And many companies do the mistake of saving money. They spend 1 million on the machine, or 500,000 euros. Then they save money on the tool holder and the tool. A good tool holder can have a cost of 500 euros. But then you do a good job. If you save money on the tool holder, you spend, I don't know, 100, but then you break everything and you cannot do the job. I know that it seems silly when I'm telling you, but I can assure you that some companies do this kind of reasoning. They save money on the tools and tool holders. And also this is nice for fixtures, because it is a good idea in micro to machine your part, attach it to a pallet, and then take everything and go on another machine if you want to do a next step. This has been invented for EDM. We will see that in EDM, first we have to machine the electrode, and then we have to put the electrode on board of the EDM. So they invented an interface that is really precise, not to add any error. These systems can be repositioned with errors around even 1 micron again. And for example, if you want to measure, you machine it, and then you go under the metrology machine. There is a hidden risk there is an hidden risk here. Can you say something? Because you see that the part is attached to the pallet. The point here is, what happens when I remove the part from the pallet? We know that residual stresses are a bad thing, and if the material was already stressed at the beginning because of the previous processes, and I did not apply any thermal treatment for relaxing that stress, it means that when I remove material and I detach the part from the base, it will bend in order to recover, because the residual stresses are self-balanced. So, in other words, I put a stressed part on board of the table. Then I remove material. Since I have removed material, together with the material, I have removed also the stress. So when I remove it, it will bend for balancing again the residual stresses. There was a nice demonstration in manufacturing processes 1. So if you attended here at Politecnico, maybe you remember it. There was a demonstration in foundry about the presence of cracks when the part decreases its temperature in a mold of foundry. And this is strictly, what I have said is strictly related. So what you can do is having a good material, so you should apply a thermal treatment, so it is completely relaxed, so you don't have any fear then. Or it is an issue, because the risk is that, for example, I have some examples. I have one in particular. Let me see. Yeah, I cannot do this part. I have done already this part. That is the last part of the presentation. I will do it the next time. But let me tell you about this case. It comes from the military field, so I don't like this point, but let's take just the good part. In a company, I have told you already, that company machining the wings of the F-35, it is a piece of aluminum. They have to reposition it up to 12 times in order to recover the residual stress. Because they put the slab the first time, they do the roughing. When they remove them, they remove the fixture in order to machine the other side, it bends. So then they do the next step. So they are approaching the final shape step by step, because every time they recover the residual stresses that are coming out. And so if you find a solution for reducing the number of times they have to replace, they would save a huge amount of money. So this is an interesting thing to solve. Okay, I think, yeah, I can stop here. I just have to say something about the behavior of the machine in terms of core error, but I will do this in the next lecture, which is tomorrow. See you tomorrow. Sì, sì.
Hai parlato di Quarkbacks. Sì, non ho capito cosa siano. E Pave, in italiano è Pave. E diceva che un altro trattamento che si può fare è dare un altro passato oppure io...
Sì, si chiamano fluidi criogenici. In sostanza uso un fluido a bassissima temperatura che raffredda a tal punto da infragilire il materiale. Quando il materiale è fragile tende a rompere la bava naturalmente. E quando è utile invece che piuttosto che rompersi si deforma e crea queste bave. Le volte anche molto grandi.
Grazie.
Un giorno posso sì, sì. Aspetti che chiudo qua.